Okay, so I'm going to be talking today about AutoML in the real world. So if we think about AutoML and what it means to many of us in the academic community, we think about efficiently identifying models, architectures, features, hyperparameters that allow us to make good predictions on various benchmark tasks. We have a controlled benchmark, we're building these systems, and that's how we build cumulative knowledge. Now, while in industry you cannot, I'm not suggesting that one cannot build cumulative knowledge, there are a lot of other factors that we need to account for in practice. So, for example, machine learning is organizationally distributed. There isn't just one person working on a machine learning model. There might be hundreds of people working on a particular stack. And each one of them is contributing to a little piece of that stack. And so we need to coordinate efforts across that entire process. And so that might involve making systems that don't usually work together. It might involve allowing people to make complex trade-offs in their product, or something that is very common in the literature now is things like hardware-software co-design, where we're trying to come up with neural networks that have kind of small architectures that fit into small devices or edge devices. So there's some awareness of this currently in the academic community, but there are a whole number of other problems related to this and related to thinking about how we arrive at things that are good product experiences, where we're using, let's say, an LLM, and it comes up with something that people find satisfactory and safe. These are really complex outcomes that isn't just a single scalar value that we could optimize directly with AutoML. So I'm first going to start with talking about adaptive experimentation at Meta, so my particular team, and then I'll be talking about the practice of machine learning engineering, and this will highlight some of the ways that this might be different from how people in academia might approach the problem. And then I'll talk about 5 challenges in AutoML that are specific to the empirical context that my team has been working in. Okay. So the adaptive experimentation team has this mission to increase the throughput of innovation using AI-driven methods and frameworks. And this is a slightly out-of-date picture of our organization, but we have about 25 people on the team. We do both applied and use-inspired basic research, and so we have a number of researchers, but we also have people who are dedicated to engineering, and some people who are dedicated to partnerships and data science kind of work. And we sit within the company as a horizontal R&D function. So we're not assigned to a particular product like Instagram or Facebook or WhatsApp or Reality Labs. We collaborate with all of the different organizations, and we're not in infrastructure, so we don't have to, let's say, focus on serving gigantic models. So we can really focus across the entire company. And as you'll see, the work that we do is quite broad. And because we're doing this really broad work, it's really beneficial for us to focus on long-term generalizable research, because we want any single thing that we work on to be high leverage and to be used across many different contexts. And I think this is why it's easy for us to publish our work. When we publish papers, it's not something that is just some neat idea that we came up with. It's a solution to a real problem that we have. And by rigorously evaluating it, we know that we can transport it to a bunch of different settings and feel confident in the results. So oftentimes, we work on internal technical reports, and the paper is just a way of wrapping it up and making it consumable to other people, and then we can also get peer feedback, and that typically improves the ideas. And so we are committed to publication, and we're also committed to open source. So we run this 2 open source projects. One is called Blowtorch, and the other is called Axe. Originally, we just had one system called AE, which did both modeling and experiment management, but we created a decoupling of concerns so that it's easy for developers or researchers to develop new algorithms, and it's easy for engineers to make modifications to do the deployment. And people can kind of work independently, and then there's a really easy interstitial layer where you can stick your algorithm into Axe, and we know that we can serialize that. We could start the processes up from some kind of failed state, et cetera. So Axe essentially does all of this bookkeeping. I'll talk about that in a little bit. So our operating model is a little different than most machine learning teams. Well, we have a core platform that people can use that's self-serve. And then when we're trying to expand our scope, what we'll do is we'll identify partners who have problems that are amenable to our tools. In some cases, we can just hook them up with our software and say, hey, here's how you translate your problem into a Bayesian optimization problem. And in other cases, it might be at the proximity or some zone that is something that seems like we can solve, but we don't know quite how to solve it, but it seems like it's important because there are a number of people who have some kind of isomorphic problem. And so we'll develop those methods, we'll work hand in hand with the product teams, test these things out, see how they work in practice, and then once we have a reproducible formula, which often involves working out the math and doing simulations and things like that, because these are really expensive experiments otherwise, we'll put that into our software stack, and we'll try it out internally for a while, and then if it's stable and we're comfortable with it, we'll open source it so that the community could use it, and we can minimize the amount of churn on the API. The application areas that we work in is quite broad. So my background is in actually originally in quantitative social science doing graph mining, but then eventually I moved into causal inference in networks and randomized experiments, and then later applied statistics, and then finally reinforcement learning and machine learning. So a lot of my roots are in A/B testing, running online experiments. And so this was the first application area for us, where there are a number of contextual bandit problems that had to be solved, but these contextual bandit problems had very large continuous action spaces, and we found the Gaussian processes and Bayes-op to be really useful. And there are a whole lot of different considerations for the A/B tests, which I'll talk about in a little bit. But then there are all these other more, and the A/B tests are largely used for machine learning. This is a core part of the machine learning stack. And then at the same time, there's a lot of different aspects of hyperparameter optimization, including traditional hyperparameters, but also things like neural net architecture search, and then optimizing things like information retrieval systems when you have a recommender system. And I'll get into that some more. And then we also work on a number of other more diverse projects, like developing sustainable concrete. So we're working with people in academia and at the data centers to try to come up with concrete that emits low levels of carbon into the air, carbon dioxide into the air, but is also really stable. So we do some ML for science. We also do other ML for applied science, so designing hardware with Bayesian optimization. So these are high-dimensional inverse problems, as well as active learning for things like perception research, which is important for how we design VR headsets or AR headsets. So it's very diverse. I'm going to be focusing on the AutoML aspects, but I think a lot of how we approach the problems is informed by a lot of these other application areas as well. For those of you who are less familiar with Bayesian optimization, I'm sorry. Hopefully this is going to be at high enough of a level that most of it will be understandable. But just to give you a high-level overview, Bayesian optimization is a sample-efficient black box optimization technique where it's really meant to optimize some small number, let's say 20, but now more recently up to, let's say, 200 or 300 parameters in perhaps as few as 5 to 20 to 1,000 iterations, depending on what your budget looks like and how quickly the experiments can run. And it utilizes some kind of probabilistic surrogate model to model the outcomes of your time-intensive or resource-intensive experiment. And then you have what's called an acquisition function, which picks the next design point, the next configuration to evaluate. So typically we'll use a Gaussian process. This has really nice inductive biases that tends to work really well for a broad range of sample efficient optimization tasks. It's particularly nice for a lot of these A/B tests that we run, but we see in AutoML that it works quite well as well, right? It just assumes that if you have one configuration that's similar to another, that the relationship is relatively smooth. There are ways of having more expressive models, and that can plug in to the blowtorch framework, which is largely illustrated just in this figure. Okay, so overall machine learning at Facebook. I'm going to be describing a typical product machine learning setup. This isn't indicative of all machine learning at Facebook, but I think it gives you a flavor of how a lot of people who are working on recommender systems largely approach problems. So Meta has thousands of engineers that are working to improve the product. So most of the surfaces that you'll see on Instagram or Facebook, and increasingly, or in some cases, WhatsApp, are using some form of machine learning to rank the content and figure out what's relevant. And these teams have certain goals that might have to do with the quality of the user experience. It might have to do with engagement, might have to do with retention, how much do they continue to use the service, because we want people to have a high quality experience, because having a high quality experience means they continue to use it, which is good for the world and it's good for revenue. And these are typically less noisy metrics than revenue, so oftentimes we'll optimize for the things that are representative of positive experiences on the platform. And so there are many such metrics that one can define. And then increasingly efficiency matters, right? We have larger and larger deep learning models that we need to have capacity for. We have billions of users, and if all these billions of users are utilizing many, many machine learning models, we need to make sure that those models are extremely efficient. In order to do this, they often can't work directly with these product metrics or these even some notions of efficiency, because they need to be evaluated via some kind of randomized experiment. Oftentimes people work with proxy metrics like classification loss or maybe some kind of off-policy evaluation. And so that poses some challenges, which we'll talk about a little bit. And so for each of the systems that people are working on, there are various hyperparameters. And to give you some examples of tasks, we have things like feature engineering, so how do we design better features to put into the model? How do we select what features we should put into the model? The architecture of the neural network, how should the recommender system work? What are different ways that we can be producing recommendations? And this might involve various deep learning extractors and k-nearest neighbor algorithms. We might have to develop new recommendation policies as to how to sort the data according to our predictive model. This can be done offline or online. And then finally, once these engineers do come up with various candidates that seem like they're positive, they have to then be selected in order to be shipped. And some of these changes have to be resolved. And for each of these, there isn't one person who has visibility into all of the processes. So you can't say like, hey, like you should do this and this is going to connect to this in one way. In some other way, the way that you can make it work is through organizational processes and tools that encode the organizational processes. And here we're just talking about the product machine learning engineering, but then there's also various tasks on the infra. So there's a completely separate organization that's dedicated to things like how should we train these large models? How do we reduce inference costs so that predictions are cheaper? This might involve some hardware software co-design, which might relate to things like neural architecture search or sharding of the neural net. And then there might be some other cases where we want to reduce inference costs on mobile. So for example, there's a lot of machine learning that might take place on the device, including some amount of ranking, as well as things like natural language understanding or type-ahead models that are used for virtual reality. And again, for each of these tasks, there are many, many people. There might be dozens of people, even on a single team, that are performing these tasks in parallel. And so this causes a lot of challenges and a need for efficient optimization, because we have limited resources for ML training. So it's not just universities that don't have enough GPUs. It's also these large companies don't have enough GPUs. And so we need to make efficient use of those GPUs for training, or in some cases, CPUs might be faster. We also have limited resources for testing the models. Even though we have many users on our platform, the signal-to-noise ratios are often really low. It's sometimes hard to move a metric by more than 0.2% or something like that. So you need really big sample sizes, and so that means that only a few sets of users or developers can run experiments at the same time. There might also be other ways of doing things like testing performance. One might have dedicated racks where we can simulate traffic, and that will give us some sense of how a certain model or policy is going to respond to the load. Those are big groups of machines, and that's also resource constrained. And then there might be some other cases where we have to benchmark things on mobile devices. And there are only so many mobile devices that we manage in our lab, so all of that has to be queued up. And finally, for a lot of these things, we often have to coordinate across these. Okay, and so going back to this question, like, what does AutoML mean to you? Well, AutoML, for us, means coming up with methods that are efficiently optimizing across all aspects of development and serving in order to meet evolving needs of the company. And so this can be quite dynamic. A lot of how we orchestrate this within the company and for my team is through a tool called AXE, which is our adaptive experimentation platform. And the way that this works is that there might be other tools and services that connect to AXE, or particular developers, engineers that interact with this system. And that system is able to efficiently optimize configurations. And the way it works is that it is able to design a configuration with the help of Blowtorch, the help of Bayesian optimization, and then it can deploy it to different modalities. So you might have a machine learning training job, you might have your mobile test infrastructure, you might have your A/B test, you might have some kind of simulator or off-policy evaluation. There are all kinds of ways to evaluate these things, and one can mix and match these different modalities when running experiments. And so this is how a lot of this kind of efficient optimization within the company works. So I'm going to be talking about 5 challenges for industry scale optimization. The first is reducing technical debt in systems. So as these systems continue to grow, we have to peel things back a little bit more in order to manage it. These things become increasingly complicated and harder to maintain. They use many resources, and that might not be the optimal configuration to have all of these things that have been developed years ago still running in production. There's also the problem of coordinating across teams. If people are all creating these little diffs to the models or diffs to the stack, how do we resolve all of those diffs and put that into the product? Can we do that one-on-one, one by one? Is that efficient or feasible given the limited resources? Not really, and that's why we need Bayesian optimization. Another advantage of the system that I showed is that we can optimize across different systems that might be owned by different product teams or infrastructure teams. So for example, if we want to combine architecture search with hyperparameter tuning or hyperparameter tuning with feature engineering, we're able to do that because we're able to plug into many different systems. And then finally, I'll be talking about automating complex decision processes. So you'll see later on that oftentimes these machine learning classifiers are really quite upstream of what people care about. And so trying to perform your optimization actually exists at a much deeper level of the stack, and ideally you want to be able to propagate all that information kind of end to end, not using gradient descent through this whole process. And as it might have been clear, my team has this hammer, which is Bayesian optimization, which we largely use for most things. There are some cases where we'll work on things related to contextual bandits, but here for AutoML, I'm going to largely talk about Bayesian optimization. Okay, so reducing technical debt. There are a lot of advantages to growing complexity in the system. The more knobs that you're able to instrument, the more we can personalize experiences. We can kind of do things differently for different kinds of users. The more performance we're able to squeeze out of the system. And so naturally, there is this movement toward complexity. So here, when I mean parameters, I mean things that can be tuned with Bayesian optimization, but obviously the same holds true for things like deep learning models, where the number of parameters of your neural nets are increasing over time. So complexity is often good for the organizations in some sense, but it's also really hard to maintain and scale. And so we also need complementary tools for decreasing this debt that allows us to continue to understand how the system works and is built, and allows us to maintain these things, because each individual subcomponent can break. And so before we get into this problem of reducing technical debt, I'll be talking about some tools for making trade-offs. Because ultimately, this is a trade-off about efficiency or simplicity versus performance. When we were first working on applying Bayesian optimization to online experiments, we found that oftentimes decision makers had multiple objectives. So as I said, with the product metrics, people are looking at a handful to hundreds of different metrics simultaneously. And so we really felt that it was important to resolve this constrained multi-objective optimization problem, and then later found that increasingly for even usual AutoML tasks, where we care about inference costs and model performance, multi-objective optimization is useful. Things like, multi-objective optimization is useful. And so instead of doing single objective optimization, one optimizes multiple objectives. And this is characterized by the Pareto frontier. So in this case, we have this non-dominated set of designs. So each of these axes is an outcome. So let's say this is inference cost and model loss. And maybe the inverse, the negative, because here we're maximizing. And what we want to do is push this Pareto frontier out. And one way to do that is to operationalize this as hypervolume. And so the idea is that you have some reference point. So you've got some corner. What is like the worst loss that you care about, and what is, you know, the worst inference that you're willing to take, and that's your reference point. And then what you do is you compute the volume or area between that point and your Pareto front. And so this is really easy to imagine in 2 dimensions. It's also really easy to compute in 2 dimensions. This is called hypervolume, and there's an acquisition function called Q, hypervolume improvement, that allows for doing this in batch cases where you can simultaneously deploy multiple tasks. So here, what we're trying to do is find a set of points that increase the expected improvement, this like full area above the Pareto frontier. And then there are ways of doing this when outcomes are noisy. So sometimes training is stochastic, or if you have things like reinforcement learning and you're trying to evaluate a reinforcement learning algorithm, oftentimes those are really stochastic, and A/B tests are stochastic. So we also care a lot about these noisy settings. And so there are also adaptations that one can make where we're able to integrate over our uncertainty in the existing Pareto frontier, because we might not actually know which of these points are truly along the frontier or what values they're taking on. And later on, I'll be talking about some more tools about making this more efficient. So just to give you a preview as to where we're going. Here in 2 dimensions, it makes sense that we might want to present a decision maker, an engineer, with these trade-offs. This is easy to understand. But in general, this is exploring a lot of things that people might not care about. So after the fact, you'll show them the Pareto front and they'll be like, oh yeah, these things in the corner are clearly really bad. And they don't really know that they don't like the things on the corner. And so ideally, we can involve the human in the loop somehow to just directly kind of go along that arrow that takes us to the regions of the space that they're happy with. And that becomes increasingly important as we have more objectives. So if we have, let's say, 5 objectives, there's exponentially more surface area that we have to cover with the Pareto frontier, and it's almost impossible for a human to understand that, and it's going to become really inefficient. Like even random search will have like a similar number. Maybe we'll have like half the number of non-dominated points compared to doing Pareto front optimization. So this is really inefficient. And later on, we'll talk about a solution to that, to scale to these higher number of objectives. But for the sake of reducing technical debt, we can really just think about 2 objectives: efficiency and model performance. So the first thing I'm going to talk about is a method for introducing sparsity into hyperparameters. So there are particular cases where we might have some kind of status quo where we don't want to mess around with the configuration too much. Imagine that you have all of these compiler flags. You've got hundreds of compiler flags, and you've got a production system. Your engineer isn't going to want you to change 80 of these knobs at the same time. Similarly, if you have this complex machine learning setup where you have all kinds of different information sources that you can be getting your recommendations from and all kinds of different parameters for your policy, you might not want to change all of these at the same time. And so what we want to do is come up with some kind of trade-off between sparsity and the objective. And so in this particular case, I'll be talking about targeting feature level sparsity. So some L0 penalty where we want to make the minimum number, we want to modify the minimum number of parameters in order to achieve a good outcome. And so as an example, from some of our simulations, and we've seen even better results for some real-world tests, we might be able to improve the objective almost as much by modifying many fewer parameters or setting a bunch more parameters to 0. So this will become a little bit more meaningful in a minute. So let me give you an example of a simulation that mimics a realistic environment used in recommender systems. We have this notion of sources, these things that are producing different kinds of recommendations. Recommendations based off of the people that you follow, based off of your friends, based off of your inferred interests. There are all kinds of ways of generating recommendations, and we call each of these a source. And when we're ranking, we retrieve some number of items from each source. And so there's this number, right? And when that number is set to 0, we don't need to query that source anymore, and we could just get rid of it. And so when we think of sparsity, we think of just wanting to make as many parameters 0 as possible, at least if we're able to achieve similar performance. And so if we were to just use standard Bayesian optimization, it doesn't know anything about the sparsity. So if you're trying to optimize 25 parameters, it will very rarely, it might explore the corners a little bit. So you might get a few zeros. But in general, it's not going to find solutions that are sparse. Most of the good solutions are going to utilize the entire vector. If we use a model that encourages sparsity, so there's this SAS prior that uses a half Cauchy prior on the weights that's been really useful for Bayesian optimization in recent years. This introduction of sparsity into the actual Gaussian process can result, just incidentally, in cases where the number of active dimensions is a little bit lower. And so we can find solutions that are able to achieve, let's say, half the number of active parameters. And this method that we propose, which is essentially to do multi-objective optimization on the loss function and this L0 penalty term, allows us to find this Pareto frontier where we're able to have maybe, let's say, only 5 active sources. So that's cutting down the amount of resources needed perhaps by a factor of 5 and get pretty comparable performance. And this is just an example of what happens underneath the hood. You'll see that it's able to identify the sources that have the highest quality and essentially cut off all the ones that are low quality. There's another use for multi-objective optimization, which is feature selection. And this involves another set of techniques if we're doing discrete optimization or doing combinatorial optimization, where you have a number of features. Let's say you've got 300 features in your model, and it might be difficult to evaluate what is the true cost of this feature, because the cost of the feature might involve, let's say, retrieving a whole bunch of items from a database, and there might be heterogeneous costs and maintenance costs to each of these. And so in this case, in our simulation, we have some distribution of features. I think it's just kind of made up, but it's empirically motivated. And we have an SVM that has 300 hyperparameters a bunch of them have to do with whether or not the importances of the features, and then the others have to do with some hyperparameters. So it's this mixed search space. And so the goal is to get rid of as many features as possible to reduce the cost, and also select the hyperparameters that allow you to do that. So this is an example once we combine this particular kernel. This is a kernel that we had proposed in AI Stats 2023 by Arwin Deshwal and colleagues, where we're able to represent binary spaces really well and then optimize over mixed search spaces. And then we're also able to not just model that data, but optimize the acquisition function, because optimizing that acquisition function itself is a hard problem. And so once we combine these two technologies, we can see that we're able to recover these Pareto frontiers that minimize the cost of the features and the model loss to an extent that is much better than just doing, let's say, feature selection, where we're using feature importances and cutting off at different thresholds and then optimizing the hypers. So by doing this all jointly, we can find a much better outcome. And this solution is completely general and works for any kind of model and any kind of setup, including setups where the evaluation costs are quite expensive. A lot of these technologies turn out to be useful for other things. So for example, we have this other situation where there are many proposals to model changes. So for example, you might have a number of different people working on feature engineering. So coming up with transformations of features, adding new features into the ML models. We might have people who are developing better training procedures, all kinds of data augmentation procedures. We might have new architectures to the multitask models that we're using. There might be new policies for how we translate those predictions into a ranking. And all of these changes could potentially interact. So maybe we could ship them one by one, but we don't know if that's actually optimal. And since everybody's working on these things in parallel, we might as well evaluate them together. And doing so might be necessary because we have limited testing resources. And so before we were using Bayes-Opt for this, people were doing this process by hand. You had what was called the chef, who oversaw the master cook process. And the chef would pick out different changes, different aspects of the diff that they think are promising, and choose the ones that they think should be combined. And then they just test a few of those and pick whatever is best. So this is very time-consuming for somebody to figure this out, and it's also clearly not efficient, at least if we don't think that people have the expertise to do this efficiently. And so the solution is the same solution that I just presented. It's combinatorial optimization. So one has a kernel over these binary features, and we can use Bayesian optimization to optimize the objectives. Oftentimes, these are for product metrics. And so we can utilize multi-objective optimization when doing this combinatorial optimization. So the last challenge that I'm going to talk about is decision-making with complex objectives. So many experiments are run at Facebook each year. I think this is an old statistic. Sorry, by Facebook I mean Meta. At Meta each year. This is a very old statistic. This number is probably even greater, but there are tens of thousands of randomized experiments that are being conducted for every possible change. Whenever we introduce a new product feature, whenever we introduce new changes to the machine learning model, this has to be tested to understand what the value is and what the trade-offs are. And as I said, just because we have many individuals using the service, a lot of the outcomes are high variance, they're really skewed. And then they're also it's really costly to collect the data because you have to run these experiments for, in some cases, weeks, because we care about the long-term effects. We don't care about the short-term effects. If we optimize for very short-term effects, we're just going to be maximizing clickbait and things like that. And so if we are in this regime, what people tend to do is just run large experiments, just test a few different combinations. If we think about that master cook process, we have the chef that just picks out 3 candidates to test out. But we know from previous experience, time and time again, that there's huge returns to testing out more configurations. You don't want to just test out 3 hyperparameters and call it quits. You ideally want to test out dozens if you're able to afford that, and if you're able to do that efficiently. And what makes this really complicated is that we might have dozens of outcomes that people keep track of. This is an example of a tool that people use to analyze A/B tests. Each one of these rows is a metric that I have anonymized. And in this experiment, we see the red line is the mean, and the blue thing is the confidence interval. In this case, the experiment does nothing. But you could imagine that you have a lot of cases where these are overlapping with 0, and so it's not clear if there's an effect. And so it can often be like reading tea leaves when you're trying to make sense of these things. And when we run these A/B tests, we always see that there are trade-offs. Anytime that you're running an experiment, whenever you're optimizing, if you ever just optimize for one objective, something bad happens, right? So let's say that we're just trying to increase engagement. This might put a lot of load on the servers, or might put a lot of load on mobile devices. And if this is happening, let's say in an emerging market, that data could cost people a lot of money. And so it might not be worth it to make that trade-off. But we see that there's a lot of value to the exploration. So here is the status quo. That's what's currently in production. And we can see that there are things that don't change engagement. They don't change any product metrics substantively, but at the same time are able to reduce costs. So there is this Pareto frontier that exists of logical outcomes. And when we initially, as I said, when we initially started doing this, we were thinking, okay, maybe we can just come up with an equation, just ask them for a linear combination of how much they care about each metric. People don't really like this. It's confusing to them. You especially put this in front of an engineer, and they'll be like, who are you, nerd? Like, don't give me this sciencey crap. Instead, something that makes sense to people is constrained optimization. And because a lot of the way that people think about this is that they have some primary goal, and then they have secondary goals that are kind of guardrails. But the problem is, once we have a lot of guardrails, the feasible region becomes really small, and they also don't really know how to interpret the guardrail. Like, if we say the guardrail is that this metric can't change, that this metric has to be above a 0% change, that means that we have to improve that metric in a statistically significant way, at least depending on what your cost function is, or your penalty term and your constrained expected improvement. And so when people try this, it gives them results that they don't like. And so the solution that we came up with utilizes preference learning. It utilizes pairwise comparisons between multiple outcomes. And so what we do is have this flow where people run some initial randomized experiment, and then we show them some set of outcomes from their experiments or some simulation of their experiments. We have this Gaussian process surrogate and can show them a bunch of counterfactual results that resemble real-world trade-offs. And then we can simply ask them, which of the two do they prefer. So this is increasingly common, as you've seen with like RLHF and things like that. These pairwise comparisons can give you a ton of data. And so, more formally, if we were to characterize the setup, we have these decision makers who have some limited time and patience for playing this game using this interface. And they're usually willing to give it about 10 or 15 minutes. People are surprisingly patient with this. And it doesn't take that long to perform this task. It takes about 10 to 15 seconds for, let's say, 15 outcomes. So people are relatively fast at this, and we can feasibly collect something like somewhere between 40 and 90 comparisons in a typical session. And so we are able to collect a reasonable amount of data, especially if we're able to produce these recommendations in real time. So the goal is to learn this utility function that we can optimize instead of some scalarization equation or instead of identifying the Pareto front. And how should we be focusing the user's attention when showing them the pairwise comparisons? So if we think about this kind of toy setup, we might have two different outcomes. We're now thinking about stuff in the outcome space. So the input, we're going to be modeling some kind of latent utility that is a function of the y's, of the outputs. And you might have some underlying surface that is the true utility function if you knew it at all points. And within the range of possible interventions that you could do, you might not actually be able to achieve certain goals. Like there might be some points that a person wants to optimize all metrics simultaneously. That might not be possible. So there's some kind of feasible space that exists that we don't know a priori. And ideally, what we want to do is not explore spaces that aren't feasible. So we don't want to just show people outcomes that are just chosen IID at random from a hypercube, right? That would be collecting a bunch of data where there's no support. We know that our experiment is never going to achieve these outcomes because certain outcomes are highly correlated. And so this human-in-the-loop setup works in this way where we run our initial randomized experiment. We have our different combinations of machine learning models. We have these different parameters that we're using in our ranking policy that we're interested in testing. We deploy that fully randomized initial design. And then we can ask users about their preferences with respect to this surrogate model. And then we can perform Bayesian optimization without any human intervention. In some cases, for each batch, and recall that this is an A/B test, so each batch might take weeks to run, we could ask them at every batch to update their preferences, but we find, at least in our simulations, it's not necessary. We could just learn the objective once, and it's good. And so the way that the process or algorithm that we're proposing works is that we don't actually know what the feasible region is, right? We're not going to choose this bounding box, but we're instead going to compute what we think is the feasible region based off of posterior draws from our Gaussian process surrogate. And so we make a draw from this multi-output Gaussian process, and then we perform some optimization of this. In particular, we're going to ask people about queries that have high utility, so we're going to show them points that we think are good. And that way we can learn about what their utility is without actually knowing exactly what outcomes are achievable, because we know approximately what outcomes are achievable. And so we have this one-step optimal strategy for learning the user utility, and the idea is to show comparisons that help us maximize F. So the idea is to show queries to users that allow us to learn the objective efficiently. It turns out this has a nice analytic closed form. And we can run this. We can estimate people's utilities. These curves that we produce in practice correspond to how much people care about it. Like, people will look at these plots and be like, oh yes, this is intuitive. And then when we do it, it does result in better outcomes. So in our paper, we have some synthetic examples, and in reality, it seems to work quite well. I believe I'm out of time, so thank you.
Thank you. We are indeed out of time, so in the interest of time, I'm going to just ask just one question. Everybody here at the conference and in this room is like an expert in machine learning. And so which I think we may sometimes lose sight of the fact that, lots of our target customers may not know anything at all about machine learning. And so in your role at Meta, I believe you must deal with many users coming to you that may not even understand what it is that you can do for them, right?
Yes.
And so I was just wondering if you could comment some on the challenges that you face in developing these kinds of tools and interacting with, your user base with that kind of broad expertise and interests and understanding maybe of even the tools that you can develop.
Yeah, I mean, one important aspect is just persuasion. I think people are often skeptical of these tools because they have a bunch of experience and they think they know what's going to work the best, and they also just feel like they don't have the time to learn a new tool or run this iterative set of experiments. And figuring out how to reduce those frictions is really important. And so having solutions that work well for everybody's setup, and we're incrementally, trying to identify what those are, and having things that work automatically and just produce the right results can be really helpful. And because things like Bayesian optimization, AutoML, are less mainstream than just neural networks, people are less willing to put time into making it work. So people will just try it once, and if it doesn't work for them, then they'll never use it again. And you've lost a bunch of capital. And so it's really important that people have a good product experience. And honestly, a lot of this, we have to go to individual teams and reformulate their problems as an HPO and then just show them the interface, and then they can go from there. But it does require a little bit of hand-holding. I hope at some point we could get to a point where we don't have to do the hand-holding, and I understand that there's some efforts being made by people here and taking just descriptions of the data and coming up with an AutoML plan, and that's pretty exciting.
If only we could automate the social aspect of things, we'd be, the world would be great. Okay, so anyway, please join me in thanking our speaker, Eytan, again.